Shall we start now? So, good morning to everybody, and I hope that you have a wonderful session before the tea break. Continuing my lecture from yesterday, today I would like to focus more on how this future distributed electricity network based on microgrid should operate. So, in this today's lecture, I will try to conclude what we have learned previously. Previously, we studied that we need to have renewable energy system with more and more integration of renewable energy sources. In the first lecture, we tried to understand at very high level how the off-grid energy system should be designed, taking into account the available energy resources at that particular location, taking into account the available load profile information of that particular location, and then based on the load prediction, based on the energy resources prediction at that particular location, based on the historical data, how they can help us in finding out the optimum techno-economic sizing of system components which can help us to fulfill sustainable energy demand of that particular location. And for that, we also discussed briefly how this operational characteristics as well as the availability of energy resources which we need based on the prediction for doing the analysis, for finding out the optimum sizing of system components by considering replacement of the system components over the lifetime of the system, and then we discussed that how we have to calculate net present value, and based on that how we can calculate levelized energy cost and find out the solution which should be more economical as well as in a position to fulfill the technical characteristics. And also then we discussed that how such type of off grid is going to be connected with the main grid in the future, and then how we have to design or how we have to develop different operational characteristics of that microgrid when it is going to connect with the main grid in the future. So, we will continue that, and then also briefly we discussed about sustainable energy conversion using hydrogen as an energy carrier also. Okay. And in that also we tried to understand how this machine learning techniques can help us in doing the prediction of hydrogen production based on the renewable energy sources, and then how that green hydrogen production can contribute towards the different application of hydrogen, including automobile, process industries, and so on and so forth. Then also in the last or in yesterday's lecture, we discussed about one European Union Framework 7 project, in which we tried to understand how the scalable energy management infrastructure for aggregation of households can be there, and how we can utilize centralized approach, that is the virtual power plant approach for managing the demand of group of houses through aggregation based and shifting the operation of non-critical power intensive load, and for that how we have to include ICT infrastructure that we studied in the last lecture. So, all these things which we are discussing now, right. So, considering the key focus of our course on sustainable technology development, then now I am going to take it forward to see how we have to redesign or how we have to change the configuration of future electricity network when such type of off-grid system are going to be connected with the main grid. So, they are going to be operating as a microgrid, but with interface to the main grid. So, there are lot of things which we need to work. We need to create a toolbox with proven technical solutions which can be deployed rapidly and cost effectively, and which can enable the existing grids. Now, it is a very important point to enable the existing grid to accept power injection from all energy sources. Okay. So, this point what it has been said here, it is a very important point here. It means that when we are talking about different energy sources, and especially when we are talking about the distributed electricity network, it is going to be a big challenge. We need to provide a technical solution which can help us to operate that particular distributed electricity network, maybe as a microgrid. Okay. It means the concept or the methodology which we discussed in of the off-grid system, how that has to be modified when we are connecting it within the electricity network, that we will study. So, when we want to connect, it is not only the technical parameters which we need to take into account, but at the same time we have to consider about regulation and commercial framework for facilitating trading, means to ensure that all we will in a position to accommodate with wide range of operating situation. It means that this is again a very important point when we are operating this different type of energy sources within distributed electricity network as a microgrid. So, what type of regulation and commercial framework should be there? Because within the microgrid also we are going to have lot of distributed energy resources, energy storage also. So, they also want to make the profit. So, for that profit, right, what type of trading mechanism should be there which can help us to have more and more renewable energy sources within the distributed network, that we will study. At this moment, most of the platforms, they are available, but they are not having that much capability to do the planning and development of network, taking into account the stochastic nature of distributed generation both in steady state and under dynamic condition. So, here under the dynamic condition, you can see that if we have load dynamics, and with reference to the load dynamics, if we are going to have the intermittent renewables also. So, how we have to develop some analytical tools which can help us in understanding the intermittency of renewable energy sources with reference to the load dynamics also, and then here our objective is to operate it as a grid connected microgrid. So, whether we will be requiring any dispatchable power source within that distributed network, right, to overcome this dynamic condition and to operate this microgrid more as a self-sustainable unit. So, you got the point now. So, here maybe I should explain, I missed to bring the my document camera, but maybe here briefly I will explain you. So, when we have this microgrid here, and in this microgrid, when we have all different type of renewable energy sources, energy storage of course we are going to be there, load dynamics is going to be there. So, all these things are going to be dynamic, and then of course, this microgrid is going to be connected to the main grid also here, but here we want to operate this microgrid as a self-sustainable and taking into account the transient or the dynamic conditions, and to make it more self-sustainable, here we will need one distributed generator which should have the capability to dispatch the active and reactive power as per the requirement within this microgrid to make it more self-sustainable and reducing the demand which we required from the main grid. So, that point have been considered here. Now, another very interesting point, the second point, it says that we need to have differentiated definitions of grid connection requirements for the various types of generator because of their different operating characteristics. When we discuss about the integrated renewable energy system based on hydrogen as an energy carrier, that was one example. There we noticed that each and every component, they were having very different operational characteristics. Due to that, when we want to make the grid connection for different type of generators, right? So, we were going to require different type of definitions or the codes or the regulation depending on the source which we are going to connect. So, that is also a very challenging also. Then we need to establish shared technical standards and protocols, okay, which will ensure open access, enabling the deployment of equipment from any manufacturer. Then this point is very important, and we discussed this point in the last lecture also, how we have to develop ICT system for utilizing innovative service arrangement to improve energy efficiency, control, management and trading. Yesterday, through this SEMIA project, we have studied about the energy efficiency, okay, and for that energy efficiency, we used ICT infrastructure for shifting the operation of non-critical power intensive load. So, similar ICT infrastructure which we can use in this microgrid also for controlling the power flow from different sources, but at the same time doing the trading within this microgrid also. For that also we will need information communication technology infrastructure. And now, when we are having all these different type of sources with different operational characteristics, and then of course what I mentioned you, we will be integrating them in the existing grid, and they are going to be mainly operating on the AC microgrid architecture. So, we have to make it that how successfully we interface the new and old design of grid equipment, so that interoperability of operation and control arrangement should be there, right. So, considering all these factors into account, we need to develop some infrastructure or new architecture design for that one. So, that design we will study today. Is it okay? And today's our focus will be how we have to operate future distributed energy network using ICT infrastructure, taking into account the existing methodology, right, that will be basically AC microgrid architecture, which can help us for further integration or further promotion of renewable energy sources. As we know that in India also there is a lot of incentives are given and lot of policies are there for promoting solar photovoltaic system within the distributed network. So, at this time the policy doesn't say that whether this solar photovoltaic system which will be installed on the rooftop, whether they are going to contribute only on injecting the power or they will operate to manage the power. So, at this point what I have observed through the policies what the government of India has published, they have not shown or they have not mentioned that when we are having very high number of distributed generators, in this case it is the solar photovoltaic system, how they are going to impact the power quality within the distributed network. So, there is a lot of points which have not been carefully or technically addressed by taking into account the next 20 years future also. So, that is why we need to have the young professionals and young engineers like you who can think for let us say for the next 25 years ahead, that if such type of system is, and of course, they are going to be there. So, what type of technical challenges, operational challenges which we are going to face within the network. So, that is what here we need to have new architecture, new concept for promoting integration of solar photovoltaic system, and for that then of course, we will need to utilize the machine learning for doing the forecasting techniques and the customer participation, because we have to see that in let us say in next 10 or 20 years how this system and how this architecture can help us. And then for that also we will need some innovative energy management strategy which can help us to increase the penetration, energy storage and demand response, and through SEMIA project yesterday we try to understand the demand response also. Then another next point which is a very important, that is effective distribution control for the benefit of power quality and reliability enhancement at the connection point. So, here at the connection point, when this distributed electrical energy network, future network, when it is going to work and going to get connected to the main grid. So, let us say if we take this as an aggregated one unit, so at this connection point we have to see that how the active and reactive power is going to be managed within this distributed network by taking only the active power from the main grid and reducing the reactive power capability here, and then at the same time we have to see that this microgrid, like because here we are going to have very different type of operational characteristics, and of course we can do the forecasting techniques. So, with the help of the forecasting techniques we can have the complete detailed tentative analysis like how the power generation, load profile it is good. So, due to that how the power quality is going to be impacted. So, that is a very important point. So, this power quality it is going to be correlated in two parts, maybe related to the active power and related to the reactive power also. So, with reference to the real power, it may go on the harmonics also, whether we are in a position to operate at the synchronous frequency or not, or otherwise what type of harmonics will be generated and how it will impact the power quality of the distributed generation. Similarly, when we talk about the voltage quality here, so the voltage quality is also going to be very important because it is going to impact the voltage variation to the main grid. So, therefore, here you see with the help of the forecasting techniques, when we will study that how the renewable generation is going to be there, how the load profile is going to be there, with reference to that how this power quality parameters are going to be changing. And then when we are taking this complete microgrid as a future smart distributed network integrated with the main network, let us say if we take this point of common coupling, right. So, we have to see that at the connection point how this active and reactive power management is happening. Okay. So, this is a really interesting point when we are talking about the sustainable technology development and especially within the distributed network. Now, here we discussed many things here. So, to have integration of all these different things, different parameters, we need to use system engineering approach to study the operational integration of distributed generation and active customer participation. So, here active customer participation, it is basically going to be like most of the houses in future, they may have building integrated energy system, for example, the solar photovoltaic system, and due to the IoT techniques, we may be in a position to shift the load operation of the selected non-critical power intensity load, taking into account some incentive based demand response. So, then that is why we call it here active customer, and with reference to that we studied in the last lecture. So, you see, when we are talking about smart distribution infrastructure, how it is going to be there. Now, here, so this diagram is from one of my research article. Okay, it was published long back when I was working in South Australia. So, here you can see that. So, what the discussion which we did, so this discussion is mainly focused on this distributed smart grid network here. And we had to see, like, because you have good understanding and you got some very good inputs from Farooq related to the machine learning techniques also. So, you can see that how those machine learning techniques which you have learned or which you have got some idea, right, how you can implement in this operation of distributed energy network for making it more smart and operating it as a microgrid. So, here what we defined here, let us say within the distributed energy network, we want to promote distributed renewable energy sources. At the same time, we want to do the demand side management, that also we discussed. So, how all this and of course, the energy storage are going to be there. So, all these different components, right, need to be automatically controlled. So, here you can see that one should have microgrid central controller, okay, which should be in a position to manage the power flow within this network by reducing the demand on the network. And of course, we know that this microgrid may not be in a position to fulfill the complete requirement of the power. So, we are going to get some of the power from the main network. Okay. So, that has to be limited to the real power only. So, when we are limiting that to the real or active power, but managing the reactive power locally, we are improving the energy efficiency of the upper side network also, and having more energy efficient operation. So, now here this is a very interesting point, because our existing power system network, right, they have the limited capacity, okay, and of course, as per International Energy Agency analysis, it has been said that, I do not remember the exact figure, but the huge number of electrical network or transmission lines will be installed, okay, but with what purpose? But with the purpose of to have more integration of sustainable energy technologies, for example, high capacity wind power plants and like that. But now here we have the focus that within the distributed network, how we can manage, right, the power generation, load management, reactive power management within that particular microgrid. So, here you can see such type of microgrids, there will be n number of microgrids, they will be operating in parallel. So, every microgrid is going to have its own central controller. Then from the supply side point of view, this is going to be a point of common coupling, and this controller has the duty, right, how this local management is going to be there. For doing the local management, here you can see that how the data informations from different sources is going to be collected by this microgrid, and how the local management of the power going to be there, that we are going to study now. Okay. And what is the objective? Objective is to reduce the demand on the main grid and to make ourselves more self-sustainable communities. That was the focus that was the main focus of our yesterday's lecture. So here you can see that we may have different type of energy storage. Some of the sources, here this is a very good point, some of the sources is going to be dispatchable power source. Otherwise, we may not be in a position to do the complete power management here. So how we are going to do that one? So now this diagram is further modified here. So I believe that this diagram will help you in understanding how the different electronic components or power conditioning devices are going to be required in integrating such type of sources. So I believe that many of you are having the background in electronic devices, components and electronic engineering. So you can see that how different power conditioning devices are required for integrating all these different type of sources within the microgrid. So here I will explain you. Let's say this one unit is there, or one distributed electrical energy network is there, which is connected to the medium voltage network. So here all these different sources, they need to have their proper integration and intelligent operation also. For that we need here at this point of common coupling microgrid central controller. So this microgrid central controller has the responsibility to control these local microcontrollers, okay, for different sources and the loads also. From the utility point of view, utility is going to contact with the microgrid central controller also. And for that, then we, of course, we need some distribution management system and load controller also, because we studied yesterday for doing the demand side management. So how we are going to do that one? Now that is the main question now here. I am going to explain you what type of characteristics which we need to implement in doing the operation of this dynamic operation of this microgrid with reference to all these different conditions into account. So here, if you might have carefully observed here CHP is there, combined heat and power plant unit. So we assume that, let's say, heat requirement is also there. But let's say if we consider our Indian tropical condition, we may not need to have the heat within the distributed network. So we can have maybe simple gas turbine or micro turbine also. So this micro turbine or CHP unit going to be in a position to provide the power within this microgrid as per the requirement. Okay. So that requirement, like how it is going to be fulfilled, and that how this microgrid central controller is going to communicate that or going to implement that, that we are going to study here. So here you might have observed that. So here we have n number of components with different operational characteristics, and this microgrid central controller here. So this microgrid central controller is having a very important role. Okay, it has to enable the decentralized active network and using the local control of distributed energy resources. It means that if we go back here, so here it has the duty, right, to control all these sources, but for what purpose? The purpose is like to have the reliability of power supply within the distributed network, okay, then by giving the promotion to increase the consumption of renewable energy sources, then of course to have more autonomy for local system management, and it should have the capability of islanded operation and synchronization to the main grid. So here you can see that I have that work also, but we don't have the time. So if suppose this microgrid is in a good position to operate under the islanded condition, right? So this microgrid central controller should have that capability here. Okay, so that is the important point here. But let's say when again we want to connect it back to the network, then it should be in a position to do the proper synchronization also. So that's what in the first lecture we mentioned about the off-grid system, and then that off-grid system needs to be connected to the main grid system, and it is going to happen into the future. It means that this microgrid central controller, it is going to play the major role on that one, right? So here you can see that how this future sustainable technology development is going to be there, and how this future sustainable technology development is going to be integrated into our existing energy system network. And many of you are having very different background, that I know that. So in future, as per the statistics, most of the engineering requirement is going to be in the sustainable energy technology, because there is a huge requirement of going to be huge requirement of professional engineers in next 10 to 15 years. Okay, because our complete energy infrastructure is going to be through sustainable energy transition. So while doing your work, okay, you can focus that how you can contribute your expertise towards that, and of course finding appropriate employment opportunities also. So I mentioned this point also, right? Energy efficiency by coordinating consumption of energy. Forget about it, let's say the power. And for that already we have seen a big project, that scalable energy management infrastructure for aggregation of household. And now this system, the microgrid which we are talking here, let's say, is going to be a test system for future technology, because in the future whatever the technologies are going to come, like fuel cell, electric vehicle charging, or many other distributed sources, that will be integrated within this distributed network. Now the very last point, this point here is very important, right? That point, it says that virtual power plant and for the trading. So from the network point of view, now from the network point of view, this complete system with different operational characteristics integrated together within the microgrid. So this microgrid should have the capability to operate it as virtual power plant. And we use that word in yesterday's lecture also. So now you can see here that how this virtual power plant is going to help for efficient participation, not only from the power management point of view, but from the energy market point of view also. That we are going to discuss very soon. Now if we go back here, we have seen the what operational capability is going to be required for this microgrid central controller, but at the same time we will need to have capability of controller in each area. So this is a again very important point. So when we take the controller in each area, okay, within the energy system or whatever the system we are taking into account here, it should operate for a particular standards also. So for a particular standards means it should maintain the voltage within the limit, okay, and frequency variation within the limit, and it should be in a position to optimize generator schedule and controllable loads also, right. So that the data which will be collected from each controller is going to be used for forecasting energy demand and availability of renewables also, and then accordingly doing the optimization of this network, okay, to have the minimum interruption within this local area as well as with the main grid also. And within this microgrid area, we need to maintain complete power balance and of course the energy balance with reference to the time both also. So that point, right, is very important. And now here you can see that the points which I discussed, what the role is going to be there, like, and how their efficiency and effectiveness is going to be there. So unit controller is going to be very small, cell and microgrid controller will be at that above that level, and then above that we will be having the distribution management system, and at the transmission network at the higher level we are going to have this higher energy management system, right. So for doing that we need to develop some mechanism for trading, tariff, real-time control and automatic control. Now I am going to explain you, I have given you very high level overview about the technical challenges, operational challenges which we are going to face within this distributed network when we are operating as microgrid. So when we are operating as a microgrid, and this microgrid may be owned by some utility company or maybe some another company, right, because it is going to be a big technical challenge. So the company which is going to be operating or this system as a microgrid, right, so they also want to make the profit also. So how that business model is going to be incorporated with reference to the variation into the load, that we are going to discuss now with some flow chart. Okay. Now here this is a very interesting flow chart which I have developed maybe around 15 years before, and this diagram or block diagram I can say is very interesting. Okay. Now I will explain here what it says: system and market operation in a smart grid for distributed generation and real time purpose. Okay. Now we have this microgrid central controller. I will go back a little to the previous. Try to understand this one. This will give you really a very good overview to you how we have to do the operation. Okay. Okay. So here this is a microgrid central controller. Okay. So this microgrid central controller has the duty to do the power balancing within his distributed network, and we want to make it more smart. And of course we will put some information communication technology IoT based system for data communication from one point to another point. Now here in this microgrid central controller we have many sources: photovoltaic, this plant, this plant, this plant, energy storage and like that. So every unit, let's say take a micro turbine, it may have some capital investment, and based on that capital investment, lifetime of the project, energy cost, we can calculate, that is a levelized energy cost. So now here the promotion will be given to the renewable energy sources, demand side management will be there. So now the load variation is happening here, and renewable generation is also varying. Now this microgrid central controller has the duty to overcome the intermittency of the renewables load dynamics by taking the power from the dispatchable power source. Let's say this micro turbine and the CHP, or maybe from the fuel cell. So how it is going to be done? That has been explained in this block diagram. So every dispatchable power source, for example micro turbine or the CHP, it is going to require some fuel also. So naturally some operational cost function will be there, correct? And the price of this DER, distributed energy resource, we can say as a dispatchable power source, its price is going to be depend on the operational cost function. When this microgrid says that needs more power from these sources, because more load dynamics and more load generation is there, so there should be some energy pricing balance also, because everyone want to make the profit. So this source may offer some price to the microgrid controller. You can say that next 1 hour, due to the forecasting of the renewables, forecasting of the load, how much deficit is going to be there. Based on their deficit, this unit can calculate how much operational cost is going to be there, right? And taking into account initial capital cost and other functions, levelized energy cost, to make it more profit, the price will always be offered above the levelized energy cost. So that price will be offered to this microgrid central controller. So that here we have shown only one unit, but then previous slide we have seen that there may be multiple sources there. So the multiple sources, they may offer the price. Then this microgrid central controller may agree to that price or may not agree to that price. But that agreement of the price is going to depend on technical characteristics also, that we will see in the next slide. Okay. So then let's say then this microgrid central controller offered some other price, okay, and depending on its group functionality that we will study, then this unit may get accept that price and provide the power output based on some generation settings and the load. Are you able to understand? So this is a very interesting point, how this complete mechanism is going to be happening within this microgrid with reference to the cost function also, but now we will study the technical function also. But this is a really interesting how this one need to be, now you have to keep in mind how this one need to be implemented with the technical functionality, that's what we call it group functionality. And if we take that group functionality into account here and the cost functionality into account here, then you can see that how the system variation is going to be there. So to talk about the sustainable energy technologies and their development, we need to consider like this such type of microgrid approach also. So now here you can see there is a one graph. Okay, it may not be necessary to be linear, but just to explain you, I have kept it as a linear function here. Here we have the energy price from that particular dispatchable power source. Now you have to keep in mind, from that particular dispatchable power source, where we want to have more and more renewables, okay. So those renewables are going to get the priority, okay, and their tariff mechanism will depend whether it is a feed-in tariff mechanism or any other like that. But the main control of the power balancing is going to be from the dispatchable power source. So how it is going to happen? Like here we have the energy price and here we have the active power output. So with reference to the previous slide, you might have noticed that the price is going to be basically depend on the operational cost function. And when we are getting more and more power output, more and more fuel will be consumed, right? So naturally, the pricing is going to be increasing if you are consuming more and more fuel. Or why we are consuming more and more fuel? Because we want to have the more power output. So now here you can see that. So within that particular distributed network, based on your forecasting techniques, which you have studied at very high level or got some understanding, we are in a position to understand how the load demand is going to be predicted, how the renewable predictions are there. So if we use that short-term prediction, based on that short-term prediction, we will be in a position to know that in the next 15 minutes or 30 minutes, how much power demand is going to be there and how that power demand is need to be fulfilled from this source by limiting the power supply from the main grid. So let's say the system is operating, or that source is operating at this point, and the price was this, and then of course here if we come to the second point or the second graph, so this is, here we have the frequency and here we have the power. So in our engineering terminology we call it as a group functionality. So this group functionality, I teach that group functionality in one of my course where I teach stability and control, especially with increasing penetration in renewables, and we derive all these equations also there, but here we will not do that one. So let's say here we have some setting here, right? Generation setting was here, and with that generation setting the system was operating at the rated frequency. But now due to change in the demand within that microgrid, the change in demand within that microgrid, okay, so microgrid central controller has to request dispatchable generator to provide more power. So if I am an independent generator operator, I will see that whether it is profitable for me to sell the electricity or not, because that system also want to make the profit. So then that profit is going to depend on this cost function. Let's say initially we were here, okay, and system was operating here at the rated frequency, but now power is increased. So new power setting is here. Earlier power setting was here, but the new power setting is here. So if we go to the new power setting and if we don't change the settings or input setting to this generator, frequency will drop based on this curve. Okay? So if we have this drop in the frequency based on the increasing demand, that is not allowed. Right? So that is not allowed because we want that every system should operate under the standard frequency or a standard condition. So if we take that standard condition into account to avoid that drop into the frequency, right? So new setting is going to be here, and this graph and this graph, this is in the having the same slope. So this graph will move in parallel to this point, and then it moved to this point, okay. Then with reference to this new point, because it has to move into parallel to overcome that drop in the frequency, and with this new power setting, you can see that the price is going to be different. So that price with the new setting is offered by that distributed generator to this microgrid central controller. Okay. So this is a very interesting point here. You can see that we are trying to do the proper balance between the energy pricing and the power quality or the technology terms also. So this work I did maybe around 15 years before, and now the same approach is going to be implemented into the AC microgrid architecture also. So I feel very happy. and I was teaching this one when I was working at University College London. Now here you see, with reference to this new setting, this price is offered to microgrid central controller because now it has to consume more fuel. So that then depends whether microgrid central controller is going to accept that price or not. Maybe earlier the price was here, but now the new price is this much. You got the point now? So if that microgrid central controller doesn't accept this price, says that no, I can buy the power from you, or basically it is for a very short period of time, let's say 15 minutes. So if I buy the power and then into multiply energy, time and then energy, right? So maybe say that I don't want to have that much price, I want to have this much price, right? So then this generator, distributed generator operator is there, can say yes, based on let's say this price what you are offering me, I have this much setting and I can contribute. So here then he can say that I can contribute only this much load, not the complete load from here to here. So then this microgrid controller has to go to another distributed generator. Then this microgrid central controller has to go to another dispatchable source here, right, how to do the balance. And then the cost function of this another unit and the true functionality of another unit is going to be different. So here you can see that how the continuous power balancing with energy pricing dynamics is going to happen. Is it okay? Are you able to understand? So here, now I have given it very high level, then of course we need to do lot of calculations and a lot of mathematical modeling for all system components and like that. Okay, then it requires a lot of effort, but here if you are in a position to get high level knowledge or high level information, how the dynamics is going to be happening within this distributed network with reference to the load variation, and how this microgrid central controller can help us to managing that power balance within this distributed network, taking into account for profit or the income of this dispatchable power generation sources. So this is a very unique work which I did long back, and I tried to give you at a very high level so that you can get more information, but then we did some implementation on this work also. Okay, so this what we here you see how this is going to be the continuous function for different dispatchable power sources, and these functions can also be implemented within the off-grid system also. Let's say within the off-grid system, if we have n number of sources and there will be some controller and n number of sources owners, may be different, okay. So everyone, whenever they are installing any technology, so nothing is free, right? Everyone want to make the earning, whatever the capital investment we did, we want to recover that one, right? So for that you see how this pricing function with reference to the operational cost function, and then how this microgrid central controller can manage, right, by taking into account this functionality. In real practice, this graph, okay, price versus active power may not be linear, but this one, this graph, frequency versus active power price is always linear. And now here you see, to distribute or to go to the new setting, this group function is going to move in parallel. So its slope is going to remain the same. And then this same Drup functionality, is going to be used for sharing the load among different distributed generators also. For example, if I take the change in frequency on this axis, power on this axis, let us say generator, dispatchable generator 1 this side, dispatchable generator 2 this side. So, this may have this characteristic, this may have different characteristics. Okay. So, now let the system is operating at rated frequency here, let us say F0, but now we have drop in the frequency, let us say F1, let us say that is the change in the frequency. So, this change in the frequency now, why it is happening? It is happening because we want to have more and more sustainable technology or nature dependent technology integrated into the network. So, the load is changing and the load is directly proportional to the change in the frequency. So, this based on this change in the frequency, we will see that how the load distribution is going to be happening between these two different generators. So, here just I have shown you the technical function, right, let us say P1 here and this side P2 here, but on this one we can implement this pricing function. Then based on their pricing function and the agreement with the distributed generators, maybe we can have different settings here. Let us say this generator is in a position this much, and then accordingly how we have to dynamically adjust that one, right. And that dynamic adjustment is going to be based on the pricing accepted, but with the focus that the operational frequency of that distributed network or microgrid should be at the rated frequency. Are you able to understand? So, in future, right, our distributed energy network is going to be operating, in my opinion, using this concept. And to implement this concept, you have to see that how you can contribute using your technical knowledge. We are going to require a lot of power conditioning devices. So, let us say very simple. Let us say here. Now, here you can require many type of controllers, DC-DC converter, DC to AC converters and like that. So, there and then some of the sources I have taken, let us say more like a rotational sources, but some of the sources may be non-rotating type. But non-rotating type sources, for example fuel cell or battery banks, they can also contribute towards the dispatchable power source. So, when this non-rotating type sources which we are integrating it within the microgrid, we will need power electronics component or electronic component. So, this non-rotating type component, mainly the stationary, will be having DC. So, we will need DC to DC converter and then DC to AC converter. So, that DC to DC and DC to AC converter should have functionality to operate as virtual synchronous generator. To operate that as a virtual synchronous generator, then it is going to be the big challenge. So, with reference to that, one of my students, he did the work and then he implemented that work, right, and his thesis was awarded as best thesis by Agadar Energy in some southern Norway. So, because here you can see that, of course, now I had to motivate you for doing the work on sustainable technology and using some controller techniques and like that. But when we want to do the real work, okay, how we have to get it focused. So he did that work especially at this level, and his thesis was awarded as best thesis also. And maybe let me see if I can see here the work. Yeah, so he, or maybe this is much better. So then you see, maybe through the block diagram you can understand more clearly. Mostly our system will be three-phase. So three-phase to, when we have three-phase system and a rotating system which we are converting, and we have to integrate some non-rotating system also. So then for that we will need this Clark and Parkes transformation also. And I believe that those who might have been working on electronic components, and especially with reference to the three-phase system, so they know that how we have to do the conversion between three-phase to rotating two-phase, and then rotating two-phase to stationary two-phase system. And that stationary two-phase system, right, it is going to be for the stationary sources, non-rotating sources, and they have to convert it into back. And when we are controlling that, you see, then we have to implement this frequency droop characteristic. So we implemented two frequency droop characteristics there. One was related to the active power and another one was the reactive power. So here it may be little very high level for you, but I will share with you what I can say, the published work of that candidate. Okay, that is very, very good work. Okay, so now you can, means taking into account very high level how the idea which we discussed here, when we want to implement them into the work, right? So basically most of the devices need to be operated as virtual synchronous generator, and their virtual synchronous generator operation, like if we go back to this slide, okay, let's say this energy storage or the fuel cell. So here power sharing, right, based on the their operational characteristics, price versus fuel consumption capacity characteristics, or let's say cost function and frequency versus power droop function, and then they cannot immediately go and supply the power, but the decision has to take by microgrid central controller, and to take that decision from the microgrid central controller, right, it has to be based on the pricing. Is it okay? Are you able to understand, or very high level? So yesterday one participant, she was asking about the controller which need for this, let's say any of the source, right? How we can develop some embedded system based on that functionality. So here you can see, right, in that control system or embedded system, right, all these things has to be done automatically, right, without human intervention, because it is going to be making the decision in fraction of seconds of time, right. So for that, then when we are developing some controller, so basically it is going to be some embedded, whatever the algorithm we are developing, we need to get it embedded in a device. Like for example, yesterday we talked about home energy management gateway. So that home energy management gateway decision was through this Devolco product gateway, and it was of our mobile size. So in that we implemented all the functions, right, what we want, how we have to do. So similarly, these functions, not only these functions, but the functions which are going to be required, let's say, let me go up, the functions which may be going to require here that need to be programmed in that embedded system. So you can see that how this, what we are discussing, how we need to make a proper programming using, let's say, Java or any other platform, getting it embedded in that one, what information we need, what outputs we need. So that is also a very good work. So here you see this is a grid. Okay, maybe now I will try to explain this diagram with reference to this one. We have the grid, okay, but then grid is always AC. We will make it AC to DC because we want to reduce the reactive power from the main grid, only active power. So we will operate it AC to DC and DC to AC converter through that way. So here you see, when we are talking about here the interface with the common point of coupling, we will need AC to DC and DC to AC converter and inverter, and their role will be mainly to take the active power from here. Okay, and then here when it is going to provide the here basically DC to AC, so this source with reference to the microgrid is the main source. So it is also going to have a droop functionality. So that droop functionality is having the very high slope like this. That needs to be implemented there also here, because we have to do the load sharing. And within this one, right, is not necessary that 100% fulfillment of power is going to be there. Some of the power will always be taken from the main grid. So that main grid power we have to minimize, and to improve our efficiency, we will make the reactive power 0, only take the active power here. That's what my student implemented there. So then here this system, or with reference to this point, this system is going to work as a very high capacity generation source, and it is going to have the droop functionality like that, but that slope will be very high, just like a parallel to the power. Is it okay? So here you can see that when we are doing this integration with medium voltage to the lower voltage, or connecting this microgrid with objective of energy efficiency and making this system more self-sustainable for the power, right? Here we need to include AC to DC and DC to AC converter, and in that DC to AC converter, when we are controlling their PWM switching signals and like that, so that controlling of the switching signals is going to be based on group functionality. Is it okay? And now then again the power dispatching from the main grid to this microgrid from here to here, again it is going to depend like how much generation available here, how much load demand is there, what is the deficit. We are not in a position to fulfill this one, then only we will take it from here. So we are going to have a reliable power supply. And for that, then of course this microgrid central controller here need to have the information for next 24 hours ahead also. Accordingly, then from the energy balance point of view or market balance point of view, can communicate that information, okay, to the more upper level here to the distribution energy market operator. So I tried my best to explain you like how the microgrids or distributed generation which we studied or tried to study understood in previous lecture, then how we have to integrate them within the main energy network. So learning from today's lecture is going to help you right towards the sustainable technology development. And of course we have seen that not only the Indian government but most of the governments in all over the world, they are promoting distributed renewable energy sources, for example solar photovoltaic and like that. But now we can see that how the technical and operational challenges are going to be there. So to overcome those technical and operational challenges in next 20 years, we may need to find out new architecture for operation. This, in my opinion, this new architecture of operation is going to be based on AC microgrid. That's what we discussed today. And in this AC microgrid operation, now you can see that how you can contribute towards the different aspects based on your academic background and interest also, and how you can involve your young generation or the students, right, for getting trained and contributing in such type of things. Do you have any question or any doubt? Just please feel free, because we need to have some discussion. Always it is not good to have unidirectional information, because now we are talking about the microgrid. So we are talking about bidirectional information. So we want to have the lectures also bidirectional, not unidirectional. Okay. So active engagement is always important. We are doing the active engagement from the consumer side also, active engagement from the distributed sources to the main source also. So in the same way, I need some active engagement from you also. Yes, please. Speak a little loudly. Members means? Oh, you mean persons? Oh, so that persons, it depends, na? Like, I mean, if because it is at the university level, it was work was there. So we collected all the information from the utility company, and then that student, based on those information, developed its algorithm, switching signals, and like that. So that one was a PhD work. So basically, it is I think one PhD student, he did that work, and then couple of master students were also involved in that one. Yeah. And of course, then if suppose we want to have such type of system in our Indian condition, for example, so you have to consider, let's say, because you can take one typical distributed network, and for that typical distributed network, if utility company is in a position to provide the network parameters, okay, then we can do the load flow calculations of that area, and after doing that load flow calculations of that area, we can calculate how much energy storage, how much solar photovoltaics are going to be there, if suppose some fault is happening, how the islanding condition is going to be there, and how we can use some machine learning algorithms for that one.